Okay, so this was the statement we set out to prove, and we again want to point out what our P and Q is because we're going to prove this directly. So P is actually this statement here. A and B are both even. A plus B is also even as the statement Q. Now you notice that statement P is a compound statement. We can define it as P1 and P2, where P1 is the statement A is even, P2 is the statement B is even. So this basically means that if P1 and P2, then Q. A plus B is also even. Now A plus B is one number, so this is not two separate statements. All right, so when we start off with direct proof, we assume the premise is true. So to begin proving this, we're going to assume A and B are both even. Okay, because it's only then that we guarantee that the sum is even. So assume, so as our proof, we'll start off with assume A and B are both even. Okay, well, what does that mean? What does that allow me to say next? And again, all I've done here is assumed P. Well, that now I can define those quantities. So that means if A is an even number, then A can be expressed as 2 times some integer. And I'll just call this K subscript A, just so that I know that that's the K value that went with the number A. And then I'll also write B can be written as 2 times KB. That's just a subscript, that's just one letter right there. You could use 2K and 2J if you want. And so now we need to be able to state, well, what are KA and KB? Well, KA and KB are both integers, so they live in the family of all integers. And where did this step come from? How did we get from assume A and B are both even to A is equal to 2KA and B is equal to 2KB? Well, we usually want to justify our steps, so we'll say this is by definition of an even number. So we haven't done any black magic here at all. It's not like we pulled a rabbit out of our hat. We are using definitions now to logically break down this premise into something that involves equations. And when we have equal signs, then we can actually combine things. So the next thing I want to do is, all right, so how am I going to end up at A plus B is also even? Well, I want to show that when I add A and B, now the conclusion isn't A plus B. The conclusion is that A plus B is even. So there's nothing wrong with me forming A plus B or adding these two quantities together. So this allows me to say that A plus B, which is equal to, well, wait a minute, A is 2 times KA, B is 2 times KB, and this is really just by substitution. That's all we really did here, is we substituted in 2KA for A, and we replaced B with 2KB. Now, in order for me to end up saying that this is an even number, I need to be able to say, I'm going to write this off to the side, we need to show that A plus B is equal to 2 times some integer. Okay, well, I'm pretty close there. I see that both of these numbers have a factor of 2 in them. So I'm going to go ahead and factor out a 2. And if I do that, I'll just have KA plus KB. Okay, so all we did there is just factor. And we already see that it's A plus B equals 2 times some number. Well, the only thing that we need to convince ourselves of at this point is that this is an integer right here. That if I add KA plus KB, I get another integer. Okay, well, by the closure property that we just described, if you add together Ka plus Kb is an integer. So by the closure of adding together two integers, Ka plus Kb is another integer. And so let me relabel this I'll just say K equals Ka plus Kb. It doesn't matter what you call these letters. It could be W for all intents and purposes. But the reason I do this one last step is so that it looks absolutely, irrefutably like an even number. So in this final step, I'll just say, okay, so this was my next step after that. This is my next step was just a statement. And then my final step here is just going to be to say, well, that means A plus B is equal to, and we said that Ka plus Kb, we'll just call that K, a brand new integer. And so A plus B is equal to 2 times K, which means that A plus B is even. How do I know that? Well, by the definition of an even number, because 2 times some integer is even, and that is equal to A plus B. So if an even number equals A plus B, that means A plus B is an even number. And we could say that this is by definition. It can be written as 2 times an integer, and therefore that's what makes it even. So that concludes our proof, and we've just proven that if A and B are even, then A plus B is even. And that means we're done at this point. So logically speaking, we have to take this step by step, and we have to always try to deconstruct statements into operable mathematical statements. So saying that numbers are even doesn't, I mean, it means something, but the definition of an actual even number in mathematics is twice an integer. Okay, let's go ahead and do one more. We'll say if A is even and B is odd, then A times B is even. So let's start off by just identifying our two statements. And one of those is if A is even and B is odd. Now again, you could break that up into two simpler statements. P1, A is even, conjunction with statement P2, which is that B is odd. But it's not super important because we're not going to be doing any truth table stuff with this. When we assume P is true, we assume both of these things happen. And then this is the conclusion, Q, that A times B is even. So what we're going to do here is we're going to break up A as a definition of an even number, write B as the definition of an odd number, multiply them together and show that we get something that is even, that can be written in the form 2 times some integer. So I'll start off this proof in a very, very similar sense. We'll say, suppose A is even and B is odd. Okay, all we're doing here is we just assumed P. And we want to show that anytime P is true, so is Q. So by definition of an even number, this means A is equal to 2 times, again, use Ka, you can use K, J, W, whatever you want. You have to state what they are though. And B can be written as, 2 times some integer, which I'll call KB, plus 1. We don't want to call them both just K because they don't have to be the same numbers. They don't have to be one number apart, or 1 unit apart. So Ka could be 5 and Kb could be 256. We have no idea. We're trying to make this as general as possible. Again, you could try some examples, and I encourage you just off to the side to say, well, is this even a true statement? If I multiply something like A and B, and now I look at A times B, and A is even, let's see, 2, B is odd, 3, oh, that's even. 2 times 5, well, that's 10, that's even. Well, wait a minute, that actually looks like I'm taking 2 times some integer, and therefore that's going to be an even number. But let's make this very, very clear and explicit as we go through this logic. Okay, so this is by definition. Oh, wait a minute, but we have to say what Ka and Kb are. These are important details. So Ka and Kb are both some integers. And this is all by definition of even. I'll just leave it like that, you know what I'm saying? And now what I'm going to do is I'm going to multiply them together because I want to show that their product is going to be even. So what am I going to do? Well, I'm going to write A times B is equal to, okay, so I'm going to replace A with 2Ka. I'm going to replace B with 2Kb plus 1. And now you might even actually see at this point that you can just factor out a 2, but let's take this algebra a little bit further so we can see very carefully what happens next. So this is just by substitution. We just plugged in values for A and B. Again, notice that we didn't put in numerical values for Ka and Kb because we don't want to prove by example. Proving by example doesn't work. Examples work sometimes, but not always. So if I distribute this in, I multiply these two terms together, I get 2 times 2 is 4 times Ka times Kb. Distribute that to the plus 1, that's just 1 times 2Ka. And this is just by distributive property. And now, again, I want to show that this is an even number, so I want to ask myself, typically when you're showing something is even, can I factor out a 2 at some point? So I see that both terms, 4Ka, Kb, and 2Ka both have factors of 2 that can come out. Great, well that's 2 times quantity, 2Ka, Kb, plus Ka. And already I'm seeing that A times B is starting to take on the form of an even number. But this stuff in here, this is what concerns us, right? Because that doesn't look like just 2 times some integer. It looks like 2 times some crazy multiplication and addition. But here's the thing. By the closure property, we already have established that if you multiply integers together, you get integers. And so 2 times Ka, well, that's 2 times an integer, which is an integer. And an integer times another integer is still an integer. And an integer plus an integer is an integer. Therefore, this is an integer by closure of integers under addition and multiplication. Great, so that means that, so I'll make a statement like this just to make it totally clear. K equals 2Ka, Kb plus Ka. You don't have to do this. You could stop at this point and say, well, this is A times B is clearly 2 times some integer, and therefore A times B is even, but I don't know, there's just something pretty about writing it as close to the definition as you can. So A times B equals 2 times this whole mess right here, which we just said was K. And then now that says A times B is even by definition. And so what have we proven? Well, we started off with if A and B are even, if A is even and B is odd, if A is even and B is odd, then A times B is even. And so that establishes how we conduct that proof. So the point among all of this is that we're using clear logical steps where we do one thing at a time. And I realize that some people may do this step differently. Some would observe that you could just factor out a 2 there and not have to distribute all the way through. This is not the exact series of steps that one would need to see every time, but we do need to make sure that our steps follow from one another, because when somebody looks at a proof, they want to be able to say, okay, are there any loopholes in this logic? And the more gaps you keep open, the more that proof will get questioned.